propose the generic multi-frequency modeling and model validation method to solve or eliminate or facilitate these challenges. And the focus is on modeling and only on single.
Can you click on that?
So I acknowledge this recording. Yes, and then
click on the
here also I
make a click there. Now it's active.
Yeah, okay, and the next slide. So first, if we want to understand the interaction, or if we try to develop a model, first we should understand the interaction. And let's consider that one frequency component appears in the terminal of the conductor. And then what will be the interaction? First is the electrical components. For example, it can interact with the transformer, and then it can go through the output filter, and then it can go through the converter switches and diodes, and it can be rectified into DCD. And we will see there is some form of it in the DCD. And the second part is the control. Since the control system of the converter gets feedbacks from the voltage and current, the frequency component can flow into the control and interact with the PLL and also the control loops. And then in the end, it can appear in the control reference of the converter. And then this interaction will be fed back into the system within different forms. So this is a summary. Let's say then we have one frequency component in DCD, FDC, and one frequency component in AC control reference, FAC. In this reference 11, it is explained that when we have non-ideal DCD with the FDC component and the FAC component in the control, then we will see unwanted additional frequency components produced in the terminal of the converter. We call these frequency couplings or couplings. So in our second journal, we also explained that this process can continue in a repetitive loop, and the new components can get into DCD again, and then control reference again, and then it can produce new frequency components. So then in this journal, we explained that actually this the previous assumption for couplings can be more generalized in these forms, that we should also add the multiples of the frequency component plus minus multiples of the fundamental frequency. So having this in mind, we can now explain the proposed generic modeling. What we do is that first we provide the same situation as when we have harmonic in the terminal. So we have perturbations between positive and negative sequences at the terminal of the converter as a black box converter. And then we measure the response of the converter, and then we take the discrete Fourier transform of it. And then we transform it to sequence domain. And then we consider only the main patterns that we can observe from the response of the converter, and then we provide the generic model, this model from the results. So then, for example, in the generic form, we can see that this is the matrices in sequence domain, positive and negative sequence with the forms of here provided MFI plus MKF. So here it might seem very complicated and big matrices. So first we should also practice this in the experimental test to see if it can be simplified. So we did the perturbation test that we actually got the data for perturbation tests from NL test site from US. And one of the observations I'm showing here. So to understand this plot is that y-axis is the frequency of perturbation. For example, let's say we have 50 Hz perturbation. And then in response, we get DFT spectrum for that specific perturbation. So the plot is like color code. So the amplitude of the frequency component will be in this color code. So for example, here in this line, you see that for each frequency perturbation in voltage, we get also the same frequency from the response. Also here in this the second figure, we saw the positive sequence current response. And we see that here actually it's more visible. We see also different forms of the response, not only this one. So the rest of the components we observe are couplings. Also, we can look at the same as positive negative sequence voltage and current. And then for this practice, we observed 7 main couplings in positive sequence and then negative sequence as well. And then, as an example, we provide this model for the device on the test, 2 megavolts on the PV converter. So, if I provide a summary for this section, is that the frequency components can be generalized in this form. So, it will include the multiples of the component as well. The proposed generic multi-frequency model is in this way. We have perturbation tests. We take the Fourier transform and then identify the main couplings. As we saw in the experimental results, the number of couplings are limited. The number of conceivable couplings are limited. That is very promising. And these tests can be also done in applicable on simulation models, so that we can do the same process on simulation models. And since we did this test on 2 megavolt under PV, also we can extend it to say that it is useful for type 4 wind turbines and also convertible systems like traditional systems. And then the question is that if we can use the same approach for type 3 wind turbine. So in the next part, we will discuss type 3 wind turbine. Here what we see, this is a typical topology of control and topology and control of a type 3 wind turbine. So the main difference is this generator and also having the rotor side converter. So if you look at the possible interactions, we see that the difference from the previous types are that we have a winding and ID winding generator, and also the interaction with converter can occur on also rotor side converter. Also from the control, we have one control for rotor side, and also it can interact with the perturbations. So also we know that this the control operation of rotor side converter is actually depending on the speed, the rotor speed, or the wind speed. So our hypothesis is that a group of emissions and couplings can be also dependent on the rotor speed for the type 3 wind turbine. In this part, we will go for finding this relationship between the type 3 wind turbine and rotor speed. So first is we have studied the emissions and find this rotor speed dependent emissions using the RISO field measurements of RISO on the DT wind turbine. And we have synchronized power and rotor speed measurement by GPS system. So for example, in this figure, we can look at the output power production line together with the rotor speed. So we can see that, for example, in this range, there are for the identical output power, we observe different rotor speeds. So as a conclusion, for example, here also, if we take the 50 from that, we see that there are relations between the rotor speed or rotor speed and the frequency components. But actually, there are some deviations and it's not some line, so you cannot rely on this result. So it is better to also go for side tests. So we did the same actually in the side test. We have so tested this in front of arenas on 2.2 megavolt on the type 3 wind turbine. So here we are able to put one set point for the rotor speed, and then one set point for output production. So we know that where are the set points exactly. And then we measure this different points from this. For example, the grid side converter measurement is this point, and we see these lines here that are actually accurately can be estimated, can be detected here. different lines here that these are the sign of the dependency of the output frequencies or emissions to the stick, to the rotor stick. Also, we can, we have observed here and we provided this more extensively in research. And also we can look at the stator here, and we can also observe some similar dependency. And also this next part is DC voltage that also we observe here. And the rotor side converter, we can also observe similar patterns. And so this is a proof that the emissions, group of emissions are dependent on the rotor speed. And then the hypothesis is that the rotor speed dependent emissions can cause rotor speed dependent couplings. So our proposal is that we can even more generalize the proposed forms to have more and include the rotor speed in the forms of the couplings. And in some of the couplings, we are expecting to observe this dependency. So to do this, we have experimental tests from, here in the final version of the model is like this. So we have the generalized form for the couplings, and then we say that, okay, we can use similar matrices, but then we should add the couplings that are dependent to the rotor speed. So to also validate this and also practice this model experimentally, we have a perturbation test on a type 3B turbine to megavolt ampere at NL test site. Just to give a better impression from the test site is that here we can see this. This is the muscle of the type 3B turbine, and this is the torque emulator or rotor speed emulator. And also the AC grid will be connected for the test. So first we look at the general view. We have in these figures from positive sequence voltage and current is up to 5 kilohertz, just to see that what is happening in the whole range. And here it is not much observable for the dependent couplings. But still, we can see, for example, high frequency couplings, which is related to the switching frequency of the converter. So to understand this lesson part here, in the next slide, we will zoom in that range. So within the range of up to 180 hertz, here we can look at the perturbations and x-axis similarly the DFT response up to 1 kHz. And here we can observe that yes, there is one line that is, this number is in the paper, it is explained actually, it is coming out of this dependency to the rotor speed. And also we can look at the current response, which is more visible here. Yeah, these lines are rotor speed dependent. Also similarly, we can do the same for negative sequence current and voltage. And then we have observed 14 couplings in this result that 4 of them are rotor speed dependent, and 5 in the range of low frequency, and 5 in high frequency range. So together there will be like 14 couplings. And we propose this, and then for this test, the model would be similar like this, having considered all of the couplings. So as a summary, the generic multi-frequency modeling can be extended for type 3 turbines by addressing the rotor speed dependent couplings as well, which is in this form. So we can generalize. And from the results, we have observed the limited number of these couplings. So still, we can say that the proposal is applicable in practical applications. And also, in the other side is that this test we are already doing the perturbation test experimentally. So the results can be used for generic modeling or empirical modeling. And also we can say that the results at the same time we can use it for model validation. And so the question is that how to use how to perform the transparency test and also how to use the test for model validation. So in the next part, chapter 4, I will be presenting this our proposal for the model validation. So first, let's say this is the equivalent model of the equivalent topology or structure of the test bench. So here we have a grid emulator, and then we have DUT, meaning that the device under test that can be converted mean turbine or PV converter, and then we measure this response at this point. So the first part is the challenges of the test bench is that the impacts of the grid emulator. So grid emulator actually is not an ideal source. So it is itself a converter. So we can expect that having this in account, we can expect that actually there will be influences from the grid emulator. So first part could be the control system of the grid emulator. So here in this figure 4, we can see that this is kind of equivalent model of this DUT and grid emulator connection. So we can say that there is already also a model and including everything here for the grid emulator. And because of this, what we propose is that we should have these experimental tests in an open loop condition, just to avoid any couplings with the grid emulator or interaction. The second part is the output filter of the converter with the grid emulator itself. So here we can see that the output filter is there. So if we try to have these perturbations, it will already interact with this transformer and also with this filter. So in this figure, the transformer is part of the filter. So, and then just the last part would be the background emissions that can be generated from the grid emulator converters that should be considered. And then the second part is the impacts of the device under test or DUT. For example, one of the observations is that the control system of the device under test can include, for example, another different measures like protection measures in that account. So we cannot just perform any perturbation to observe the kind of steady state operation from the DUT. So the perturbation should be limited. And the second part is that the frequency range and in which range of frequency we can perform these tests. And for example, here the grid emulator is limited up to its bandwidth and also the bandwidth of this output filter. And the next part is that DUT output power set point. So for example, this is one of the simulation results. We see that when we change the set point, the output power set point of the DUT can be by type 4 wind turbine. The red color one is for the the blue color is for nominal power, and then the red color is for 65%, 0.6 per unit output production. So we can see that for the low frequency range, the impedance of the converter will change when we change its output set point. So this also should be considered during the test. And then the last part is the impacts of the measurement system. For example, here I provided this one as an example. This is one of the time domain and frequency domain results for perturbation test for 25S. And as we can see, for example, from the FFT part, that the amplitude of these couplings and the frequency components are very small. So the measurement equipment should be able to detect these changes, and so its resolution is very important. And the other point is that, as we can see in this graph, the noise level, there is a certain noise level in the measurements that should be also considered somehow. Yeah, somehow we should also be remove that part from the output results. So to have these impacts and challenges all into account, we have proposed this test methodology for IEC 21-4, and also we have explained it explicitly in fixed journal. And this is more or less, the flowchart is more or less similar to what we do for multi-frequency modeling. But more important is the first part. What are the specifications for the test, and what should be the range to put from this test? And to do this, we have proposed the table 3 specifications to make sure that the test results will be reliable. And yeah, for this, to provide these specifications, we have used experimental test results, the same from what we have from ML and other data, and also supplementary simulation results that I used for this specification. And one of the important parts is that the amplitude of the perturbations, for example, here we can see, should be different for a different range of frequencies, because, for example, in low frequency range, we get very high current response, so it should be limited. And yeah, this current range is for the option if we use current perturbations instead of others. And then frequency steps, so here more important is this minus, that we cannot go very low frequencies, because then it is like the more we are getting close to DC voltage, then the more we are getting close to somehow DC system, right? It will cause very high current response. And also to have a better resolution in the results, we propose to have 2 Hz maximum instead for the perturbations. And also, as we saw from the plot in the previous slide, we also propose to have different power set points. I mean, for example, here 3 different power set points to have to consider the changes in the control system of the unit. And the time range that it can start from 3 up to 11 seconds. This is depending on the resolution that we want the DFT response. So the summary and the highlights is that the proposed methodology can be used for generic modeling, and also we can use it for model validation of even the analytical models. Also, converter-based test benches can be used for voltage perturbation tests within the control and filter bandwidth. And also, during the test, the impacts of the grid emulator and DUT system and measurement system should be limited and considered results. So, as a conclusion, the proposed generic multi-frequency model uses the Fourier transform on the response of the converters against perturbations. So, using this Fourier transform, we can detect more potential nonlinearities in the converters. And the second is that significant frequency and sequence couplings can exist in the converter-based systems. This should be identified and addressed in the models. And also, as we discussed, the root cause of the main root cause of the couplings is modulation of non-ideal DC-link with non-ideal control reference. And also the proposed generic model, we categorized it in 2 groups. One is the converter connected REGs, meaning that type 4 and type 4 wind turbines and PV systems. And also the second group can be dedicated for type 3 wind turbines. So in the experimental results and also based on this analysis, first we see that the patterns of the couplings for converter connected systems are in the forms of multiples of the fundamental frequency and multiples of perturbations. But then also for the type 3 wind turbines, we have rotorsphere dependent couplings, which should be in the form of, we should add the part of this rotorsphere dependent or sleep dependent part in the form. And also one of the results is that the mirror frequency coupling is valid for all coupling patterns. For example, if we have any coupling in this form, in let's say positive sequence, we will most likely we will observe in negative sequence the same pattern with -2x0 frequency shift. So this is also very helpful for the detection of the couplings. And from the results, experimental results, we noticed that the number of significant couplings are limited, and mainly in the range of control bandwidth, and also some of them around the switching frequency of the converter. So this is promising to say that the proposed models are practical. And also we saw from the field measurements that for type 3 wind turbines, it is better to have to use test sites where we have controlled the rotary speed or torque, and also grid regulator. And at the same time, we can also use the grid regulator for perturbations. And the proposed technical specifications for perturbations are crucial to achieve the transparency results and minimize the impacts of the test environment and to an ideal grid regulator. And for future work, future research, I can say that the application and the efficiency of the proposed models can be also practiced on network systems in system level studies for future work. And, as an example, the technical brochure 766 can be, for example, the starting point. And also the proposed models can be generalized to also include and model the HVDC converters and fact systems, and then to execute this system level studies. And then the simulated study cases we did so we did some partly simulation studies to also evaluate the impacts of grid impedance, output power set currents, and the type of perturbation, and also test bench effects. These simulation results also can be verified by experimental tests. And then the proposed modeling and validation methods can be also applied. What we got from the experimental result can be also compared to the vendor EMT models to check that if we are at the same ground and understanding the result. So during this PhD study, we had a couple of disseminations. We have 5 journals that one of them is under second review, and another one is under first review, but 3 of them are published. And also we contributed to IEC 21-4, which is for wind turbine components and subsystem tests. And also there was also conference papers and other relevant publications under this EU promotion project. Some of the references. I don't recommend. But yeah, then the last slide, I would like to extend my appreciation to all of you guys, and at most for my supervisor, Mr. Paul Sorensen, because of his excellent support during the entire PhD. And also my co-supervisors, Dr. Lukasz Kosevia, and also Baham Gevorgian, for their excellent advices and recommendations. And also I would like to appreciate my colleagues at the TU in the Energy Department for their excellent support and company. And to my friends and also my family that I owe the life with them. And also I appreciate the funding this PhD, funding I forgot to this from the beginning. great, especially that we received funding from a project Horizon 2020 promotion, and we appreciate that. And many thanks to assessment committee for the excellent feedbacks and having assessment.
Not yet. Not yet.
I hope it will help. But then, yes, during PhD, I had sort of good memories, and so you can see the view and the promotion and the glow for these activities. And thank you all for joining today and so for the entire PhD. Thank you.
Thank you for excellent timekeeping. And I think we'll have a few minutes break now and then get into the question